Now, there are some instances of applying the chain rule that occur so often that it's really worth kind of running them down as special cases. For example, the power rule. It is not uncommon to have a power of a function and then to be interested in taking its derivative. So, for example, g of x to the n. How do I take the derivative of that? Well, the outside function here is the nth power, the inside is g of x. So the power rule says bring down the exponent and reduce the exponent by 1. So I get n g of x to the n minus 1. Then the chain rule says I have to multiply by the derivative of the function, which is g of x. Great. N g of x to the n minus 1 times g prime of x. If I wanted to use the variable notation, taking the derivative of u to the n with respect to x gives me n times u to the n minus 1, as you expect from the power rule, but we also have to pay the price of multiplying by the derivative of u with respect to x because of the chain rule. For example, let's let y be sine to the fifth of x, and let's find y prime. Well, sine to the fifth of x really means sine of x quantity to the fifth power. So, when I take the derivative, the chain rule for the power rule says I can just bring down the power, reduce the power by 1, giving me 5 times sine of x to the fourth power. But then I also have to multiply by the derivative of sine, which is cosine. And just to make it look a little bit nicer, just to get it back into this sort of notation, I'll rewrite sine of x to the fourth as 5 times sine to the fourth of x times cosine. Okay, this is also useful for evaluating the derivative of a reciprocal of a function. So let's let f of x be 1 over x cubed minus 1. Right now we have the quotient rule, which we could use to take the derivative of this guy. But I think it's actually a little bit faster, if we want to find f prime of x, to rewrite this as x cubed minus 1 to the minus 1 power, because the minus 1 power is literally the reciprocal. Then I apply this power rule, chain rule business. So f prime is going to be, I bring down the power, negative 1. Then I reduce the power by 1, so I get x cubed minus 1 to the negative 2. And then I have to multiply by the derivative of x cubed minus 1. The derivative of x cubed minus 1 is 3 times x squared. And so I have negative 1 times x cubed minus 1 to the negative 2 times 3x squared. Now, just to make it look like the rational function that I started with, I'm going to take the negative 1, 3x squared, put that in the numerator, then x cubed minus 1 to the negative 2, I'll put that in the denominator, and I end up with negative 3x squared over x cubed minus 1 squared. I think that's a lot faster than using the quotient rule. You know, on second thought, I don't think it's a lot faster. In fact, it's probably about as long, but I don't know. I like thinking about this this way instead of the quotient rule. Here's another thing that happens all the time. This is called a linear change of variables, at least that's what I'm calling it. That's when I have a function f of x, but I change x into ax plus b. So I'm replacing x with a linear function in x. Now, when I take the derivative, the chain rule says I can take the derivative of f as normal, but then I have to multiply by the derivative of the inside. The derivative of a linear function is just the slope. So I just have to multiply by a. So what I end up with is the derivative of f of ax plus b is just a times the derivative of f applied to ax plus b. This happens all the time. And you know, I think this is also sort of intuitive. Plus b is going to give us a horizontal shift of our graph. And if I shift it horizontally, I really shouldn't be changing the slope. Multiplying by a gives us a horizontal stretch or shrink. So our slope should be multiplied by a factor of a. So it kind of makes sense. Okay, so here's a fairly typical example. Let's let p of t be equal to 100 times e to the 3t. Let's find p prime of t. This is typical because an exponential function like this can often represent population growth over time. P, t, population time. Okay. So then if we're looking at p prime, we're looking at the growth rate of a population. So this could model something like that. All right, so when I take the derivative, the 100 stays there, And instead of having t up here, I've got 3 times t. That's my linear change of variables. So when I take the derivative, well, the derivative of e to the t is just e to the t, so the derivative of e to the 3t has e to the 3t here, but since I'm multiplying t by 3, I have to bring the 3 down too. So I get 100 times 3 times e to the 3t due to this linear change of variables, and that gives me 300 times e to the 3t. Here's another example. Let's let x be tangent of 2 theta minus pi. This is unorthodox. I'm letting x be a function of theta. Might feel a little weird, but it's okay. X can be the dependent variable sometimes too. So let's find dx d theta. Well, if this was just tangent, the derivative would be secant squared. But I've got 2 theta minus pi in there. Linear change of variables. So when I take the derivative, the 2 comes out in front like this, and then I get secant squared as I expect of 2 theta minus pi. Great. Okay, so here's your problem. Question 2. Differentiate y is equal to the square root of 4x minus 3. There are actually 2 ways to attack this using either of the methods that I just described. You can either think of this as a linear change of variables for the square root function, or you can think of this as the 1/2 power of 4x minus 3. So, okay, have at it. Okay, every now and again you might run into not a composition of just 2 functions, but a composition of 3 functions. Well, we can generalize the chain rule for 3 functions, or really for any number of compositions of functions. But let's just look at this. The derivative of f of g of h. What happens here? Well, it goes like this. The derivative of f of g of h is the derivative of f applied to the inside times the derivative of g applied to h times the derivative of h. So we sort of peel back layers. We take the derivative of the outermost guy, leave everybody else alone. Then we go to the next guy, take his derivative, leave everybody else alone, etc., until we get to the middle. You could arrive at this by applying the chain rule to f and say g of h. F could be the outer function and g of h would be the inner function. So this would be the derivative of f applied to the inner function, and then this here would be the derivative of g of h. Okay, so as an example, let's take the derivative of sine of cosine of tangent of x. So the outermost function is sine. We take its derivative, which gives us cosine. We leave the other 2 guys alone, so we get cosine of tangent of x. Then we move inside to cosine. The derivative of cosine is negative sine, so we get negative sine of the innermost function, tangent. Great. Finally, we're done with sine, we're done with cosine, and we move on to the innermost function, which is tangent. The derivative of tangent is secant squared, and so this is the final answer. Cosine of tangent times negative sine of tangent times secant squared.